derivation of work energy theorem itself. And also we'll discuss about power today, the definition and application of the physical quantity called power, which is rate of work done with respect to time. Okay, so first of all, let us look at the concept of potential energy. Okay, generally denoted with the symbol U, capital U. So potential energy is a form of mechanical energy for a system. It is the energy which is associated for a system with the what we call the configuration or state of the system. So as we discussed, for example, for a spring attached to a block, the potential energy, the elastic potential energy of a spring U, it is a function of x, where x is the extension or compression of the spring. Now, what that function is, we'll learn later, but what we mean by saying that it is associated with the extension or compression or with the configuration or state of a system, this is how it applies to a spring system. Okay. Similarly, when we talk about an object moving in a vertical situation, okay, then the gravitational potential energy of that object of mass m, it is a function of its height from the ground. It is going to be a function of h. Okay, so here the height from the ground from ground level is the state of the system, state or configuration. Here, extension or compression, this is what denotes the state or configuration of the system. Okay, so once we've understood the definition of what potential energy term means, we will look at the mathematical formula of how to calculate potential energy. Okay, so now calculation of delta U, that is the change in potential energy during a certain system. Change in potential energy. This occurs when a system undergoes a change in state or configuration. So in order to change the configuration or state of a system from some initial state, let's say I, where the initial value of potential energy is Ui, to a final state, let's say denoted with F, where the final value of potential energy is UF. So in this process, the change in potential energy, or delta U, which is the final potential energy minus the initial potential energy, can be calculated as the work done by the external agent. So delta U, which is the change in potential energy, so it's final minus initial value of U, this equals to this quantity. Okay, it equals to, so the change in potential energy is calculated by working out this quantity, the work done by an external agent to change the state of the system from I to F. From whatever initial state to whatever final state. That is what we use to calculate the formula for delta U for any given system. Now, how to apply this in the case of the spring or in the case of gravitational potential energy, we'll discuss that in a moment. Okay, but this is the general definition, that whenever some system state or configuration is being changed from some initial value to some final value, the work done by the external agent in the process, how much work we have to do to change the state of the system, that work done is equal to the change in potential energy of the system.
Sir, can you explain again from the when the system undergoes a change in state?
Yeah, we'll take examples that will become more clear. Right now, just write down this definition, that whenever
No,
the
sir,
state of the,
actually, my internet connection went down, so I had to reconnect from my mobile.
yeah, so just write down what I've written, that delta U is equal to the work done by the external agent. That means whenever some system's configuration is being changed from some initial state to some final state, in the process, the work done by the external agent is equal to the change in potential energy. And so that's why I've written that delta U is equal to W external. Understood, no?
Yes, sir.
Okay. Okay, so as per this definition, let's understand one example of how to calculate.
So once
Yeah.
again,
Yeah, Sanvi, to answer your question, I mean, that is how the definition actually works. Okay, that if we are doing some work as an external agent on a system to change its configuration, so what is happening to the work that we are doing? What it's converting into? It's converting into potential energy. So that is why the work done by the external agent is equal to the change in potential energy.
Okay, sir.
So when we put this in practice with a couple of examples, you'll understand this better, why it's exactly equal to that. Okay. Okay, done with this? Finish now? Okay, so let us see the application of this definition in one very simple direct example. So suppose we have this situation now, that we have a spring, an ideal spring or spring constant K and length, natural length L, like this. Okay. Now initially it is at this state. Okay. Now we want to apply some external force on it so that we are able to extend the spring from this state to this state. Suppose the extension is by D. An external force like this is used, is applied to extend the spring. But we are doing that extension very slowly so that there's no kinetic energy involved. From its natural length L, that is x equal to 0, to an extended state L plus D. So at that point of time, the extension becomes D. So find the work done by the external process, external force in the process, and the change in potential energy of the spring in the process. So realize actually here, the work done by the external agent is equal to the change in potential energy, because F external is acting in such a way that it changes the configuration of the spring only. It does not contribute to any kinetic energy or anything else, because it's extending the spring very slowly. There is no change in kinetic energy of any mass involved. So that is why the work done by the external agent is purely contributing to changing the potential energy of the spring. So now let's understand how we'll calculate this. Okay. So we can see that initially the spring is at natural length. So what about the tension in the spring? That's also 0. Tension, or you can call it spring force, that's also 0. But at some intermediate time. Let's say
Sir, once again, sir, how is tension 0, sir, for the spring?
the formula for tension in the spring is given by Kx, where K is the spring constant.
Yes, sir.
That is a property of the spring, which we've seen before, and X is the extension
Distance, yeah.
or compression, whichever be the case. Spring force applies. This is the restorative spring force.
Yes, sir.
That kind of thing. Okay, so now at some intermediate time, let's say the spring is extended by X. So obviously, now there is some tension in the spring. So F external at this point of time is equal to the tension in magnitude. So F external is equal to Kx. Okay. So now, in a very short duration of time, so let's say this is at time t equal to t. Now at time t plus dt, suppose what has happened is that the spring has got extended a little bit more. Now this is, the extension has increased by dx. So in the process, this small displacement dx in this direction. So how much work the external agent has done? Okay. So work done by the external agent for this small displacement is force into displacement. So the force's magnitude is kx and the displacement is dx. So it's a variable force. So we have to use integration, okay, to find the total work done. So now finally, when you reach the goal, which is to bring the spring up to a total displacement or total extension of d. Okay, so this is finally when the extension of the spring becomes d. Okay. So to go from initial, where x is equal to 0, to final state, where x equal to d, the work done by the external agent is this quantity. So it is integration of kx dx from x equal to 0, which was the initial state, to x equal to d. So we can see that the work done by the external agent is equal to half kd square. So for example, here, suppose we have some values given to us. We can plug that in and we can calculate the work done in joules. So let's say here, additionally, it is given that the spring constant is suppose 20 newtons per centimeter, and the extension we are giving the spring is 5 centimeters. So d is equal to 5 centimeters. Then we can eventually calculate the work done. Will be half of 20 into 10 raised power 2, because we will convert the spring constant from Newton per centimeter to its SI unit, Newton per meter, into x square. So x will be 5 into 10 raised power minus 2. So d, which is 2 centimeters, sorry, not 2, 5. So 5 centimeters will be converted to 0.05 meters. So on converting everything to SI unit and doing the calculation, we get the work done in joules. And that you can see here will become 10 raised power 3 into 25 into 10 raised power minus 4. So I believe it will become 2.5 joules. So this will be the work done by the external agent in the process. So this particular spring, which has a spring constant of this much, 20 newtons per centimeter, to bring it from a state of x equal to 0 to an extension of 5 centimeters, how much work we have to do? We have to do a work equal to 2.5 joules. Yes, if we want to restore it back also, in that process also, the external agent has to do a certain amount of work, and that will be equal to delta U. But now if we want to restore it back from 5 to 0, or from x plus, L plus 5 centimeters to L, you'll see that the external agent will do negative work. Okay. So that's why we'll eventually what we'll understand is that to take the spring from natural length to some extension, we are increasing the potential energy of the spring by doing positive work on it. But now if we allow the spring to go back to natural length, the spring is doing positive work. We are doing negative work on it, and therefore the potential energy is again reducing to zero as it goes back to the natural length. So we'll come to that, but first let's understand this whole process, the work done by the external agent.
So,
Yes.
could you please explain that you have written in the blue pen?
Which one? The work done by the external force, that one?
Yes, sir.
Okay, so work done by any force in one dimension, how it is calculated? By integration f dx? What no? F dot ds integration in general. So in 1D,
Yes, yes.
it just becomes f dx. No? Now, how much is the f over here as a function of x? It is kx, no? That we've seen in the above diagram.
Yes, sir.
So at some point of time, if the spring has an extension of x, so that extension x is somewhere between 0 and 5 centimeters, whatever it is. So at that instant, whatever the value of x, how much is the force? It is k into x. So for example, when x is 2 centimeters, it is k equal to 20 into 2, so it's 40 newtons. When x increases to 3 centimeters, it becomes 60 newtons, like that. So your force is gradually increasing as x is increasing. So the total work done by that force as x increases from 0 to 5 centimeters or 0 to d, that will have to be calculated by integration because it's a variable force. So that's why we have done that step of integration.
Okay, sir.
Right now? Okay. And then integration of x square, I mean x dx will give you x square by 2. So let me just write the steps of this integration also. So kx dx integration. So first step is you can take the constant k outside, then apply the normal formula of integration. That becomes this.
So done.
Okay, so all of you understood how the work done by the external agent is equal to a positive quantity in this case, because he's applying force in the direction of displacement, he or she, whatever.
Sir, it's
And-
left.
It's towards the right, and the displacement is also towards the right. Okay, now what about the change in potential energy? So this was the first part. The second part, the change in potential energy of the spring in the process. So for this, we'll use the concept that the change in potential energy will be equal to the work done, provided this is work done in order to change the configuration of the spring. Okay, and that is the case over here. No? So that delta U is going to be equal to 2.5 joules positive. Okay. So what is happening ultimately, what we can conclude is that the work done by the external agent, this results in the potential energy of the spring increasing by 2.5 joules. Okay, so delta U of the spring is equal to 2.5 joules. In this particular case, okay, in something else it might be different, but here the way the external agent is applying force to slowly extend the spring from 0 to 5 centimeters extension. In the process, the work done by him is plus 2.5 joules, and that work done increases the potential energy of the spring by exactly the same amount, because that work is not contributing to anything else. It's not contributing to kinetic energy or some other form of potential energy. The work done is only against the tension of the spring. Hence, the work done only results in the potential energy of the spring increasing, nothing else. Yeah, and I'm coming to that. Now let's look at another case. Okay. So now suppose what we do is we got the spring to an extension of this much already. I'll talk about compression also, but that will come later. Okay. And the same example, let's do a third part where what we are doing is we are at this situation where already the spring is extended by 5 centimeters, the spring of constant 20 Newton per centimeter, because this application of the external force. But now what happens is from here, the external agent starts withdrawing the force very slowly, so that the spring starts relaxing slowly. And after some time, it comes to this, let's say. So D prime is now, let's say, 2 centimeters. So the spring is allowed to relax very slowly by the external agent from x equal to 5 centimeters to x equal to 2 centimeters. Okay. So the spring is relaxed slowly from a state of extension of 5 centimeters to a state of extension of only 2 centimeters. So in this process now, find what is the work done by the external agent and what is the work done, sorry, what is the change in potential energy of this spring. So this time what is happening is that at some intermediate time when this is L plus X, but the work done by the external agent Therefore, kx dx, but from x equal to d to x equal to d prime. Okay, that's the final state d prime, which is 2 centimeters, and this is the initial state, 5 centimeters. So you can see that when we calculate the work done, it will come out to be a negative quantity because our final state has a smaller value of x, which is 2 centimeters compared to our initial state. -4 is to convert to meter square, and k is 20 into 10 raised power 2 Newton per meter. So this time we will get the work done as a negative quantity, as you can see. So from here, we will get the work done as half into 20 into 10 raised power 2 into 9 minus 25. So that is minus 16 into 10 raised power minus 4. We will get the work done as minus 1.6 joules. So this is the work done in that process for x equal to 5 centimeters to x equal to 2 centimeters to let it relax. Oh, sorry, I think I made a mistake. This is 4 minus 25, not 9 minus 25. So the value will be, it's not, the final state is not 3, the final state is 2. This will become how much now? 4 minus 25, so 2.1. So negative of 2.1 joules.
So,
Yes.
a work done is force into displacement. Over there, like both are in opposite direction. So,
That's why we are getting the work done as negative, na? Finally, see.
but in the formula, we don't have to put a negative sign.
That the limits are taking care of it. The fact that x is going from 5 to 2, na, that's taking care of the fact that the work done will become negative.
Okay,
You
sir.
understanding the point? The quantity
So
dx
wherever
is,
we put integration, we don't have to like put these signs before it.
no, because then that will become like a double negative beta. Because see, what is dx? Na? It is a change in the x coordinate. Now, whether that change is positive or negative, that is reflected by the limits of the integration. Na? If the lower limit is smaller and the upper limit is higher, that automatically means that we are going to put dx as a positive quantity when doing the calculation,
Yes, sir,
and
got it.
vice versa. Okay, so that is something you have to be careful about. That dx in general is a change in x. Now the sign of dx is positive or negative, that we will not put by hand. When we put the limits, the sign will take care of itself. Okay.
Yes, sir.
Sure, done.
Okay, so people, now from this we can generalize the formula here. The relation between work done by internal conservative force and change in potential energy. So let's understand this, which is a more general way to calculate delta U compared to what we have done before. So what we had seen, for example, that if an external agent applies force such that only the potential energy of the system is changing. There is no change in kinetic energy. Then we have, by definition, delta U is equal to the work done by the external agent. But in this case, the work done by the external agent plus the work done by the internal conservative force will be zero, where this is the work done by internal conservative force. That should be zero. Why? Because the change in kinetic energy is zero. Because this is the work done to only change the potential energy. There is no change in kinetic energy involved. So now by comparing this equation and this equation, you can see that the relation between change in potential energy and internal conservative force is this. Or in other words, we can say that if the work done by the external agent is just against the work done by the internal conservative force, then because the change in kinetic energy is zero. So for example, in the above situation where we discussed about the spring, what was happening is the above examples, F external was acting such that only the state of the system changed. So work done by this external force was negative of work done by the spring force. And that is why the change in kinetic energy was zero. That is why we can now say that the work done by the external agent, which equals to negative of the work done by the spring force, is equal to the change in potential energy of the spring. So ultimately, the relationship between the potential energy of the spring and the internal force of the spring is this. Change in potential energy of the spring is negative of work done by the spring force, which is the internal conservative force. No. So Khushi, to answer your question, in general, the work done by the external agent need not be equal to delta U. Work done by the external agent may be greater than or less than also, because the change in kinetic energy of the system may be positive or negative. But in any change, delta U will always be equal to negative of work done by the internal conservative force. This statement is universal. Whereas this statement was conditional, that when the work done is only to change the state. So that is why this is a better way to understand the definition or the mathematical formula for change in potential energy. It is the negative of the work done by the internal conservative force when the state of the system is changing. So again, I will explain this with a couple of examples and it will become more evident why this is the case.
Sir, what is the meaning of work done by the internal conservative force? Sir?
Coffee. Okay, so let's look at the application of this concept a little further now in what we'll develop as the work energy theorem as opposed to work kinetic energy relation that we've seen before. So next we will see the statement of work energy theorem. So this is applied to a system which has internal conservative forces. So we'll see examples also to understand this. Okay, so the statement of the theorem is that the work done by external forces plus work done by any non-conservative forces is equal to the change in kinetic energy plus change in potential energy of the system. So this is the work done by external forces. This is the work done by any non-conservative forces like friction. And of course, delta K is the change in kinetic energy. And delta U is the change in potential.
Sir, what is the meaning of internal conservative force?
Exactly what it says. Okay, conservative force, you know the definition of. Okay, it is a force,
Yes,
the work
sir.
done by which is independent of path. And when that force is acting internally within a system, from one part of the system to other, it becomes an internal conservative force.
So can you give an example of it?
We will do examples, I told you. First, write down the statement. Okay, so let's understand this next with an example, as I was telling you. So we will use part of what we learned about the spring and potential energy of the spring to illustrate this point with an example, that is the application of work energy theorem. So take a situation like this, that we have somewhat similar to the example we did, but different in the sense that now the spring is not directly being pulled by the force at the other end, but the spring is actually attached to a block, and that block is being pulled by an external force. And secondly, that external force is not going to slowly extend the spring, rather is going to act in a continuous manner so that the block will develop kinetic energy. So this is our initial state of the system. Okay, so initially the extension of the spring is 0. Initially the spring is at natural length. So its extension is 0 and the block is at rest. Now, at t equal to 0, a constant horizontal force F. So we start applying this to the block. Starts acting on the block. Assume that this is a smooth surface. So after some time, so this is the initial state of the spring. When a constant horizontal force starts acting. So after some time now, let's say the system has changed both its state as well as its kinetic energy because of the action of the constant horizontal force instead of a slowly increasing force. So at some time t now, while this force is continuously acting on the block, the spring is extended by x, and by now the block has a speed v. Okay. So we want to calculate the change in potential energy of the spring, the work done by the force F, and the speed v of the block when, let's say, x is equal to 2 centimeters, given that F is equal to, say, 40 newtons. Spring force is spring constant is, let us say, 25 newtons per centimeter, and the mass of the block is equal to 1 kilogram. So we have to find this out. Okay. So we will look at two options that we have to find out all these things. I mean, that is to find out the speed. Okay. For delta U of the spring, we'll directly use the formula that we'd seen earlier. That will be half kx square when the spring is extended from x equal to 0 to some x equal to x. This we have seen before. From earlier, we have seen this. Okay. That's all right. Okay. But to find v, we have two options. We can apply the work kinetic energy theorem to the block. That is, the net work done is equal to the change in kinetic energy. Or our second option, which is the option that we have just learned just now, is that we can apply work energy theorem, okay, but to the spring plus block as a system. So in that case, what we'll say here is that not net work done, but work done by external agent plus work done by any non-conservative force is change in kinetic energy plus change in potential energy. So two different ways of applying the same set of concepts Okay, but what one in context of applying the relation between work done and kinetic energy of the block in context of the block alone, and the other in terms of applying work energy theorem to the whole system, the spring plus the block as a system, treating it as a system and treating capital F as an external force. Okay, so we'll understand this in more detail. Just first make a note up to this point and make sure you understand all the aspects that you discussed here. Then we'll take it forward.
Sir, what is this?
What is what, Britain?
Sir, the red half which I have made right now. What you have written like in the
Okay, first of all, remove the marking that you made, please. Yeah. Starts acting on the block. Okay.
okay, sir.
Okay, so now at t equal to 0, a constant horizontal force F starts acting on the block. So unlike the previous situation where we had seen, where the external agent was slowly extending the spring, so the force was not constant. The force was increasing as the spring was stretching. But that's not happening here. Here, we are right from the word go, we are applying a constant force of magnitude 25 newtons. Of magnitude 40 newtons. It's not increasing or decreasing. The force is constant in magnitude throughout the motion. Okay, so let's understand each of these theorem kind of things that we can apply here. So as I said, that to calculate the change in potential energy of the spring, we just need to apply the formula. So our spring constant was 25 newtons per centimeters. So it's this much in newtons per meter. And we are looking at 2 centimeters as the extension. So as you can see, this will become 25 by 2 into 4 into 10 raised power minus 2. Right. So it become, I think, 0.5. This is the change in potential energy of the spring. But if you look at the work done by the force F, that is going to be Fx here directly, because a constant force X is acting through displacement equal to X along the force. That's what's happening here. So we are applying a force like this, and then this block is displacing through X like this. So work done by this force will be 40 newtons multiplied by 2 centimeters. So work done by F is plus 0.8 joules. Whereas the spring was going from this natural length state to L plus X. Okay, so now we have to find the speed of the block, and that is where we have the two strategies in place. One is we can apply work and kinetic energy relation to the block itself. So net work done by all forces acting on the block equals to the change in its kinetic energy. Or we can treat the block plus the spring like a system and say that the external forces plus non-conservative forces. Of course, in this particular case, there is no non-conservative force because we've taken a smooth surface below. But had there been some non-conservative force, we would have had to add the work done by it. So that total quantity on the left hand side equals to the change in kinetic energy of the block plus the change in potential energy of the spring.
Sir, can delta K can be called as 0.3 joules from this?
Yeah, you were asking something better. What was the question? Or you've calculated the speed?
Sir, from the work energy theorem, can we say that the kinetic change in kinetic energy is 0.3 joules?
Exactly. So that is the easiest thing to do here. See, what happens is if we apply the work energy theorem here, it's pretty simple because as we are moving the block like this is an external force F that we are applying. Okay. Normal reaction that the floor is applying is also an external force. Mg is also an external force. But the spring force that is acting on the block, that is an internal force. So we don't have to consider it. And there is no friction. Okay. So if we apply, if we take a system as the block plus spring, in that case, what is happening? Internal conservative force, एक ही है, that is the spring force, which is like with sign convention, it is minus kx. Okay, external forces are actually 3 in number, but only one is important because 2 of them are not doing work. So external forces are weight, normal reaction, and F. Okay, and non-conservative forces are absent. There are none. That's very useful. So now if we apply the work energy theorem to this system now, we want to find out the speed V. Okay, so it started from x equal to 0, u equal to 0, and after some time, it's reached a situation where x is equal to x, speed is equal to v. So if we apply work energy theorem, to this system now, so we'll say work done by external plus work done by non-conservative is change in kinetic energy plus change in potential energy. So here, this term will become work done by F only. Okay, why? Because mg and normal reaction do 0 work. This term is 0 because there's no friction. This term is change in kinetic energy of the block, which will work out. This is only a single block in my system, and this is the change in potential energy of the spring. So I get this relation that work done by F is equal to change in kinetic energy of the block plus potential energy change of the spring. This is the final relation I get when I apply work energy to this. Okay, now I'll just import these values. Okay, so I've already calculated the work done by external force is how much, and I've calculated the change in potential energy of the spring is how much. Okay, so I'll directly get that the change in kinetic energy. So this will be F into X. This will be half mv square because u was 0. So initial kinetic energy was 0. And this will be plus half kx square. So literally I'm getting this formula now that 0.8 is equal to half. And I think we've taken the mass to be how much? I'll just check it out. 1 kg, wasn't it?
Yes.
Okay, and this was 0.5 joules, right? So we are getting this thing. We are getting v square by 2 is 0.3. Right? So v will become square root of 3 by 5 or 0.6. So that will be like 0.7 something. V will be approximately 0.76, I think. Check out. So this actually gives the easiest way of solving this question, provided we are familiar with the formula of potential energy of the spring, which I am familiar because I've done that derivation before. Yeah, so this is about 0.77 actually meters per second. I'll also show how this works with the work kinetic energy relation. But when we come to that, we'll have to do a small integration because the spring force is a variable force. So we'll need to justify the work done by the spring by using integration. Okay, so I'm just minimizing this a little more.
Sir, it should be root of 0.6. No, how did you get root of 3 by 5?
3/5 is the same as 0.6, no, beta?
Oh, okay, sir. Okay, sir.
It's the same thing. So I'm using these values from above here, that my delta U was plus 0.5 joules and work done by F was plus 0.8 joules. So I'm using that over here and that is giving me this.
Sir, do we have to leave?
No, we have to still work out the question by the second method. So understood the calculation of speed now with this?
Yes, sir.
Okay. We'll take another 5-10 minutes discuss this. Okay, now the second alternative, as I was telling you, that we have is that we can use the work kinetic energy relation. Or apply work kinetic energy theorem to the block alone. So how that works out is that now we don't have to worry about what is internal force, what is external force, what is conservative, what is non-conservative. We have to just consider what all forces are doing work on the block. So there is the external force, there is normal reaction, there is mg, and there is the internal force that the spring was applying, but that to us does not matter anymore because we are only going to consider net work done. And that is equal to change in kinetic energy. So this net work done will be work done by F plus the work done by the spring force. Because work done by normal reaction will be 0. Work done by mg will be 0. And this should be equal to plus half mv square. So now you can see that work done by F is equal to Fx. So that is 0.8 joules, which you already know. Work done by the spring force, how much that will be?
Half kx square.
But with a negative sign with it, because the spring is acting in the opposite direction. No? With this, no? Because as the displacement is happening in this direction, the spring force is acting in the opposite direction. So there's the minus sign from x equal to 0 to x equal to whatever the final x is. So it's minus half kx square. So another thing you can see here that the work done by the spring has this relation with the potential energy of the spring. Delta U is negative of work done by the spring. So delta U of the spring was positive half kx square. Work done by the spring is negative of half kx square. It is minus 0.5 joules. So when we apply this information here, this and this information, then we get that plus 0.8 joules minus 0.5 joules. That is equal to half into 1 into v square, which will give us the same thing, that v is square root of 0.6 or approximately 0.77 meters per second. So in one case, what we are saying is that the work done by F is equal to change in kinetic energy of the block plus the change in potential energy of the spring. And in the other case, what we are saying is that the work done by the force plus the work done by the spring equals to the change in kinetic energy of the block. Okay, so by comparing these two equations, once again, we can see that basically the relationship between delta U and work done by internal conservative force is this. So delta U of the spring is negative of the work done by the spring. So when a spring is extended from x equal to 0 to x equal to x, in the process, the work done by the spring is actually minus half kx square. And that is why the change in potential energy of the spring is negative of that, so it becomes plus half kx square. So now any sort of spring mass system that we have, we can apply this concept. Okay. Okay, so hope this concept is clear to all of you people. So we can conclude this section by just making a general statement about potential energy of the spring now. Formula for potential energy of a spring. Let's look at this. So we just now saw that delta U of the spring is negative of work done by the spring force. Okay. So in general, we can understand from this that if a spring is taken from some initial state, okay, so for x equal to x1 to x equal to x2, the potential energy is going from u1 to u2, let's say. So delta U will be final potential energy minus initial potential energy, which is going to be minus of the work done by the spring force. So that will be basically equal to how much now? So when we equate this, we can see that u2 minus u1 will be negative of minus kx dx from x equal to x1 to x equal to x2. Because remember, work done by the spring is, okay, so negative of work done by the spring will have an additional negative sign. So it will become so from this now we have this that u2 minus u1 is half k x2 square minus x1 square. Bring these limits. So now from this we can say that in general the potential energy of the spring is given by this formula. Okay, so that means u1 is half k x1 square, u2 is half k x2 square, and so this becomes the final important formula for us. This is the expression for the potential energy of the spring. In fact, the elastic potential energy of a spring as a function of x, the state of the spring. So from this point onwards, anytime we are applying work energy theorem to any system where there's a spring involved, we will just directly use this formula for the potential energy of the spring. And whatever initial state to whatever final state the spring is going, we will apply this formula to calculate delta U by substituting x1 and x2 accordingly. Okay, so once again, hope this part is clear to all of you. It's quite an important derivation. Okay, this potential energy of a spring, and before this, the whole concept of work energy theorem and its application for that particular question we saw. So now please go ahead and complete HC Verma questions up to question number 32. Okay, in the work by energy chapter, finish up to question number 32 in HC Verma. We are coming towards a close in the chapter. Next time we will discuss about power and some more applications of work energy theorem. And of course, we'll discuss about the formula of gravitational potential energy, which you already know is mgh. And with that, we will close down this chapter. Okay, so we are coming towards that section. So please work on the HC Verma problems this week. Try to reach up to question 32 at least. Okay. So that's it for today's session. People, wish you all the best.
Thank you, sir. Bye, sir.
Bye.
So can you send the recording of this lecture?
Yes, I will send the recording and the notes.
Thank you so much.